So, the work energy theorem. We know from high school that work equals this, right? Where S is a little distance and Fr being the resultant force, the effective force. So the force that is actually being used to move the object we're analyzing. Now, something that is important to know is that the definition of work, some people try to plug in energy into that, fancy, but it's not really fancy. Work is simply a measurement of the physical effort. That's it. Work is the measurement of the physical effort you or something does and you want to calculate it. Now, how do I put this formula into infinitesimal terms? So dWr equals Fr times ds, vectorial, because we are working of vectors. And something else I gotta define for this video is kinetic energy. Kinetic energy we all know is 1/2 times mv squared. And a couple of people back in the 1890s, 1850s, around that time, they found out that work equals to the variation of kinetic energy. This doesn't work all the time, and I'm gonna explain by the end of this video why it doesn't work with every force. But they got to that conclusion, and I'm here to prove it because, as you may know, my physics professor, he loves to ask us to prove things on the exam, and this might very well be one of those things. So yeah, I'm here to memorize this. Okay, so we gotta integrate both sides of the equation, right? So WR equals to the path integral of FR times ds. Right, so Newton told us that force equals ma, F equals ma, right? So I can just write this, WR equals to m path integral of a times ds. Why did I take the mass out? Because the mass usually doesn't change, so it's a constant. You can take constant out of the integration of the integral, and it doesn't matter. So yeah, this is what I do. But what is acceleration? We know that it's the variation of velocity over time. So it's dv dt. Oh, sorry. Times ds, and I can write this as being, I can pass the dt to the other side, so it goes dv times ds dt. And you might be inclined to do something here which is not correct, and I thought this as well. I thought, oh, this is a very easy integral, but what you don't want to do, and it's wrong, it's saying that this equals this, right? So v dv, sorry, v dv. This is wrong because you're assuming that every single velocity vector is pointing to the same direction as the angle, and that is not correct. You're not integrating, you're integrating vectors. It's not the same thing. So there's a little linear algebra trick here you can do to turn this problem, this integral, into a very easy one. So the first thing we gotta know, I'm gonna write this over here on the side because it's not gonna be like part of the major solution. It's just gonna be an explanation of what I'm gonna do. That v vectorial times v vectorial equals to v squared, right? This is not the vectorial product, it's just a regular multiplication. So with that in mind, we want to rewrite this as a way, can I just do something here? Make it easy to visualize. So we want to rewrite this in a way that does not include vectors, right? Because it's a pain to do this. Like, you imagine a roller coaster, right? You got to integrate the work of a roller coaster. You're going through hell, right? If you're going to do this vectorial way, I don't even know if it's possible to do it this way. But anyway, we know this, so we want to try to see if this can equal something useful, right? And how do we expand on this? This is just the chain rule from Calc 1, like the derivatives, right? So you do the derivative of the first one times the second one, plus the derivative, the first one times the derivative of the second one. Now we can rewrite this as being this, right? So this is v. This equals, I can put, not going to be fancy, just going to write it the way it is. Cool. So if I put, we know for a fact that this equals this, right? Like this is v squared. So we know for a fact that this over 2 equals dv v. Aha! So I turn this horrible thing into this much more manageable thing. So I can just plug this, I can substitute this into this, right? So work equals mass times the path integral of, okay, I'm just gonna do d squared, the v squared over 2. 2 is a constant, so we can just plug it out of the integral. So m over 2 times the path integral of dv squared. And this is equal to m over 2 multiplies vf squared minus v1 squared. Vi squared, sorry. And what is this? This is exactly the variation of kinetic energy. And there we go, we proved this. So there is something I want to tell you is that there was a very famous mathematician and physicist. He was German. I really don't know how to pronounce his name, but we all know who he is. It's Leibniz. I think that's how you say his name. He is thought to be one of the fathers of calculus, together alongside Newton, and he calculated this, but he made a mistake in his calculations because he did not find the over 2 here. He just found this, right? So it was incorrect. And there is another German that called Helmets, I think. This is how I pronounce his name. Back in 1847, he was doing some sketching some stuff, and he calculated this, but didn't care at the time. But he saw a paper from Leibniz that Leibniz did not find the half over here. So he was like, wait, I think I calculated this before, but I found it 1 over 2 in front of this thing. And, well, either I am correct or he's correct. So he looked towards his sketches on his work table, looking from paper to paper, thousands of papers there, and he finally found it. And he saw it. He was like, yeah, I calculated it with a slightly different result. And what we're going to do? Well, I'm going to the lab and see who is correct. And he used an inclined plane over here. And he pulled a ball over here or whatever and calculated with his formula that the velocity that the object should be when he finishes sliding here should be 1.7 meters per second. And what he measured was 1.69 meters per second. So he was like, yep, that's it. So he published the paper and, explained how he got to this. And at the end, he was like, however, but, it was a big but this only works to conservative forces. And then a war started because everyone started arguing what the hell a conservative force is, because it wasn't really explicit on the paper. And a guy named Hertz, Hertz, the dude from the frequency, right? The frequency is given in hertz, which is 1 over seconds. So this dude over here, he said, well, to my knowledge, what he thinks is the suitable definition of conservative force is the one which work is not dependent on the trajectory, so the path. So, you know that you can conserve energy, you can create, quote unquote, create a new form of energy to balance the energy conservation on a ball falling. Because while the balling is gaining kinetic energy, it's losing something else, right? And this thing it is losing is called potential energy, right? I don't know if this is how you say it in English properly, but you know what I mean. When an object with the mass is on a certain height, it has a potential energy, right? So it loses that to gain kinetic energy. Oh, and they simply created it out of the blue because to protect the conservation of energy, and they know this worked for this case because weight, or the gravity, or if, however you want to call it, does not depend on the path you do. Other forces do, like the when you say get a ball and kick it, the how do you say it again? Friction, yeah, the friction. It depends on the trajectory you follow, right? So a longer trajectory means you're gonna waste more energy. So it doesn't work like that. You can't create it's not a conservative force, right? And then a dude called Weber thought to himself, okay, can I calculate potential energy using electric charges, right? So if gravitational energy is conservative, electric should too. So he came up with a thing called electrostatic potential energy. So let's say you have a charge here plus Q. And it generates something, and that thing generates a force on a small q particle over here with a different charge. It's same, also positive, right? And then you want to take this over here to infinity. Very far away, like extremely far away. Right? So we know for a fact that force from Coulomb equals some constant times the product between the charges over a distance squared on a vector r. We know this for a fact. And we can write this as potential energy, right? So from EI, this is not approaches from limit, this is y from I to infinity, okay, the distance. So this equals the F times dr. C, oh, sorry, messed it up here. Right? What is the energy, the electrostatic energy of something that is infinitely far away? Well, it's zero. Just think of something really far away. The distance would be so large here that it doesn't matter what you have in the numerator, the force is going to be zero. So this gotta equal minus the integral from r0 to infinity of Coulomb, right? So this is going to equal 1, of course, because you're using the same rule I wrote here. Then the vector times itself equals to itself squared, but since it's the unit vector, it's just going to be 1. And then you have minus ui equals to minus kq minus r0 infinity over dr r squared. And this is a very easy integral to do, so this is kq small q minus 1 over r from infinity from r0 and another easy limit, and this is going to equal eventually kq over r. So based off that idea, he was correct indeed that electric force, the force generated by electric field is a conservative force. So it works, right? And this is called the potential. How do I translate it? Potential Coulombian energy. I'm not here. Coulombian energy. Maybe that's how you spell Colombian energy. All right. So some demonstrations here that might be on the exam. I'm sorry if I am not good at history telling. My professor is very good at it, but I'm just, mimicking what he says. He has much in-depth knowledge on this. This is mostly for me to get the hang of things, how to prove stuff mathematically. So yeah, thanks for watching.